Hi and welcome to the third video on the chemostat. And in the last videos, we've actually seen that we want to use a chemostat to produce cells for some kind of culture if the cells are the desired product. And we have seen effectively that we can derive an equation for the chemostat based on the cell growth parameters, some experimental parameters, the dilution rate D, and of course the substrate inlet concentration rate as naught. So in the last video we actually made a lot of simplifying assumptions, such as the death rate is 0, and of course there's no production of products. So QP equals to 0. And some of these constants maybe I'll introduce later on, but for now just assume this means no production of extracellular products. So I'm saying stuff like penicillin or maybe ethanol if you are going to brew beer. So the substrate will be sugar and the product will be ethanol. So the yeast is producing ethanol. So you're not considering that case here. But let's continue and look at the case where KD is not. You can't ignore KD, which is the death rate. So let's again perform some balances on our cells, because again we want to find the steady state outlet concentration of the cells. So okay, let's do it again. Accumulation equals to in minus out plus the reaction, and we already assume that the system is at steady state and that we don't want cells in our inlet medium. So the outlet is equals to F into S, and the reaction rate is the VR of dx dt. And then we can just simply write it that ds, because we have already derived what d is. So ds equals to dx dt, and mu net equals to 1 over x dx dt, as we've explored in our last two videos. These are some exponential growth kinetics. So mu net equals to 1 over x dx dt, and mu net x equals to dx dt. Okay, and mu net equals to mu g minus kd. So now kd is not ignorable, so let's just factor that in. So we'll have ds equals to mu net into x, so that's mu g minus kd into x. Okay, sorry, this should be x. This is not substrate concentration, this is cellular concentration. And then you will just find that d equals to mu g minus kd. Okay, can you apply the Monod kinetics? Okay, so these are cell balance. Okay, so this is from the cell balance, and if you input the Monod kinetics, so you have this mu g equals to mu g max into s over s plus ks. These two are empirical constants, so you can just substitute that back into the cell balance. So the cell balance plus Monod kinetics will give you this. Okay, so this is the equation here, where you have the cell balance and Monod kinetics together. So you have this d plus kd equals to mu g max s over ks plus s. And if you look at this looks awfully familiar to something we've gotten in our last video, where in our last video we actually saw that when we have d equals to mu g max s over s plus ks, so that's ignoring the depth rate. You see, yeah? D equals to mu G max S over Ks plus S. Alright, this is ignoring death rate. We can see that the substrate concentration S equals to dKs over mu G max minus D. So this is after arranging. And you can see these two actually look very similar. So instead of having D, we have D plus KD. So wherever there is D here, you just replace it by D plus KD. And wherever there's D here, you just replace it by D plus KD. And then you can shortcut. You can do a sort of a shortcut where you don't need to do all the manipulation steps. You can just simply arrive at this. So wherever you see D, just replace it by D plus KD. Alright, because these two are so similar. So if you arrange this into this can be arranged into a similar form. So except that you just replace D with D plus KD. So let's just do that. D plus KD. Okay. And that will basically skip you quite a few steps instead of making S a subject from here and then you have to do the whole thing again manually. So this is from our cell balance and Monod kinetics. So we have sort of arrived at a very neat kind of equation already. So let's move on. Since we have this, and we still need to find what is this X. Alright, and yeah, we need to find X and we still have not found X yet. So we'll need to look at one more equation, namely the substrate balance. So again, you have the accumulation goes in minus out plus reaction. No accumulation is a steady state, just Fs minus Fs naught plus some reaction term. And then what might you ask is this reaction term? So that's Vr into ds over dt cell plus Vr ds over dt of the product. So again, we have the cell consumption. So some of the substrate is going into producing cells, some of the substrate is going to be producing product. But again, we assume this is 0. It's a simplifying assumption. So we are only producing cells now. So you have this ds dt cell. So this is the rate of cell growth, rate of substrate substrate consumption due attributable solely to cell growth. So let's do some manipulation to get back our mu g as we have done before. So this is ds over dx dt. Okay. So okay, in case you forgot, this is actually delta x over delta s. Okay, so we're just replacing this here, this term with so this yx by s is just this term, and we'll rearrange this into this 1 over minus y by y into x, y subscript x by s. So we have an expression now, and this of course is equals to mu net into x. Right? So mu net into x, so that's mu g minus kd into x. Alright? So that's your ds dt due to cell growth or cell consumption. Yeah. So this is the growth term and this is the maintenance. Okay. Yeah. Or if you want to consider using the mu g equation, we can rewrite this like this: x by s maximum, then you'll have mu g into x, which is what we have earlier derived. And since mu g, yeah, this is something we've derived earlier in the last videos, so we'll use this maximum consumption, maximum cell production rate. So this is assuming KD equals 0, but now we assume, yeah, this is assuming KD equals 0, right? So now that KD is not 0, we have assumed some of this cell growth actually goes into the net growth, and some of it is used to replace the dead cells. So this is the net growth rate, and this is the replacement rate of dead cells. So we can still use this coefficient, done in an experiment, no problem. But all we need to do is just to include that little death rate, mu net plus KD into x. So the S dt of the cell. So we substitute that back into our substrate balance. We substitute that back into our substrate balance. So it's 0 into Fs. 0 equals to Fs minus Fs naught plus Vr. And then you'll have this minus x over y x by s maximum mu net plus kd. And there we go. Now let's just bring this to the left hand side and divide everything by Vr. So x over y x by s m mu net plus kd equals to d s minus s naught. Okay, so not too bad. Looks like we do have some kind of expression for s already. We have seen this from the s equals to d plus kd, and with ks into ks over mu g max minus d plus kd. Okay, and well, we just substitute that back in here. Okay, and then we can find this s, and we can make x the subject again, and let's see what we end up with. So we have y x by s maximum for mu net plus kd. Yeah. So mu net is nothing but d equals to mu g minus kd. This is from cell balance. So that eliminates one more variable because mu g minus kd is just mu net. So x equals d over d plus kd s minus s naught y x by s maximum, where this s equals to this long term here. Of course, you can actually just write everything into this equation, although it will look very messy. I'll probably just leave it like that. But essentially, we've derived what we need to derive. So we can see that x, the outlet cell concentration, will depend largely on the dilution rate and how it compares to the death rate of the cells, and of course the usual d plus kd, monop kinetics and the cell balance are over here. And of course, did I make a mistake somewhere? This looks very funny. Okay, so this is the accumulation. This is in, this is out. So this should switch places. Okay, so this is here. Anyway, yeah. So that makes a lot more sense now. So the S will be here. Yep, so increasing S0 will increase the outlet cell concentration. Increasing the dilution rate will decrease up to some extent. And of course, it's dependent on this constant over here. So that's all we have for you for the third video of chemostats, where we assume that cell death is not negligible, and we have derived that equation. Okay, see ya.